So in this video we're going to prove another consequence of Bayes' theorem, which is the open mapping theorem. So what does this open mapping theorem say? It says that if you have a bounded linear map between two Banach spaces x and y that is surjective, then there always will exist a small ball of radius delta around the origin inside the image of the open unit ball by the map T. Right, hence the name open mapping theorem. It will send this open ball into something that contains an open ball. So let's prove that. How do we do this? Well, we're going to define yn to be n times the closure of the image of the open ball. So that's step one. I'm first going to prove the theorem, but with the extra caveat that I'm not getting into the image by T of the open ball, but I'm getting into the closure of that. So I'm defining these sets for all n. Now they're obviously closed sets because I'm taking a closure. And now I can tell you that the union of all the yn is all of y, right? Because T is surjective. So any point in y is going to have to be T of something, and so it can be written as n of T of something. Now, if the union of the yn is all of y, then it is certainly not small. So in particular, the interior of the union of the yn, which is just the interior of y, which is all of y, is definitely not empty. So by Bayes' theorem, the only way this union is non-empty is if at least one of them is non-empty. So there has to exist an n naught such that y of n naught has non-empty interior, as in it includes an open ball. So there has to exist an n naught, but also a y naught in y and a radius, let's call it r naught, such that the ball centered at y naught of radius r naught is included in n naught times the closure of the image of the unit ball by T. Right, that's good. Now, okay, so if this ball here is included in here, it also means that the ball centered at y naught divided by n naught of radius r naught divided by n naught is included in T of the B of 0, 1 closure, just by scaling. Now, if you take any point z, which is small enough, so let's say in the ball of radius r naught divided by n naught, then what can I say about y naught divided by n naught minus y naught divided by n naught plus z? Say, well, it's equal to norm of z, which is smaller than r naught over, strictly smaller than r naught over r naught. So I can tell you that y naught over r n naught plus z belongs to TB01 closure, certainly for all z small enough. All right, but I can do the exact same reasoning. I've put a plus here. I could have put a minus. So y naught over n naught minus z is in T of B01 closure for all z, and now you can subtract these two things and you get that certainly 2z is in T of B01 closure. Right, but now what else can I do? What I can say is that what it means to be in this closure is that there exists a xn and there exists an omega n, let's say, so there exists an xn in B01 and there exists a omega n in that same sequence of points in that ball, such that xn tends to y naught over n naught plus z, and omega n tends to y naught over n naught minus z, right? That's why, because these points here and there are in the closure. And now what if I take xn plus omega n over 2? So xn plus omega n over 2, that tends to z as n goes to infinity. But sorry, t of xn goes to that, t of omega n goes to that. So t of xn plus omega n over 2 goes to z. And that exactly tells me that z is in the closure of t of b01, because this average of xn and omega n will be in b01, of course. So we've proven in that step 1 that the ball of radius r naught over n naught is included in the closure of the image of the unit ball by t. And now we need to move from this result about inclusion in the closure to inclusion in just the image by t, possibly reducing this radius r0 over n0. So step 2. So for step 2, I'm going to give a name to r naught over n naught. Let's call that c. That's going to be my constant. And remark that by step 1, we have that b0c is included in the closure of tb01, but you could scale that and get that b0, so the ball that's centered at 0 with radius c divided by 2 to the j is going to be in the image and the closure of the image of the ball of radius 2 to the minus j, right? Just by multiplying everything by 2 to the minus j. So I've got that for all j. So now give me a z in b of 0c over 2. I'm going to show that this ball, if I halve the radius at least, I'm going to be in the image of the unit ball, not the closure of that image. Now, how do I do that? I use step 1, or I use more precisely star. So by star, because I'm in B0C2, there exists a x0 in the ball, the ball centered at the origin with radius 1/2, such that, okay, t of x0 is close enough to c. I mean the closure, so this, I can pick my x0 such that this is arbitrarily small, and I could pick it smaller than c over 4. But okay, but now t of x0 minus z is in b0 c over 4. So by star again, what do I get? I get that there exists an x1 in b0 1/4, such that t of x0 minus z minus t of x1, I should put a minus sign, so plus t of x1 is smaller than c over 8. And then inductively, so you keep on repeating that process, there exists a sequence xn of points that are all in the ball of radius 1, such that what happens? Such that t of the sum j equals 0 to n of the xj minus z is smaller than c to the 2j plus 1. That's one thing. And then my xn are all chosen such that they have norm smaller than 2 to the minus j, even to the minus j plus 1, but whatever, for all j in n. Okay. Now, that means what? That means that sum of xj, if you go j between some n and some m, is going to be smaller than the sum of this geometric series for all n and m in n with m greater than n, and therefore these series converge. To some x. In what? Actually, not only did I take all of them in the ball of radius 1, but I actually took all of them in the ball of radius 1/2. So it converges to some x that is in the closure of the ball of radius 1/2, which is certainly in the open ball of radius 1. What happens to t of x, the sum of the xj? Well, it converges to t of x, and t of x is equal to z, since t of sum of xj minus z goes to 0. Alright, so what have we got? We started with an arbitrary z in the ball of radius c over 2 centered at the origin, and we found that that z is of the form t of x for some x in the unit ball, the open unit ball of the open unit ball of radius 1, obviously. And that concludes the proof of the open mapping theorem. So now that we've proven the open mapping theorem, we have a very neat little corollary. If I have a map between two Banach spaces that is a bijection, a continuous linear map that happens to be a bijection, then its inverse will also have to be continuous. Now let's see how we prove this. Well, the open mapping theorem tells me that there exists a C such that the ball of radius c centered at 0 is included in the image of the unit ball by t. So that means what? That means that for every y in capital Y, if they have norms smaller than c, then there exists an x in B of 0, 1 such that y is equal to t of x. Okay. But what is that saying? It's saying that for every y in capital Y, if it's smaller than c, then t minus 1 of y has to be, because t is a bijection, smaller than 1. Okay, but we can scale that and say that for every y in capital Y, t minus 1 of y divided by norm of y and multiplied by c, say, is always going to be smaller than 1. So what does that tell us? That tells us that t minus 1 of z is smaller than 1 upon c for all z in the unit ball. And that proves that t minus 1 is indeed bounded, which means continuous for a linear map. Okay, so that's very handy because you should remark that it tells us something about spectrum of operators. Right? When we talked about spectrum in the context of Hilbert spaces, we looked at the set of all lambdas in R such that lambda times identity minus t is a bijection. And now we have, thanks to the open mapping theorem, the fact that asking for that is exactly the same thing as asking for lambda identity minus t to be a bijection and the inverse being bounded. And that's for an operator t bounded on some Banach space X. So that's going to be very, very helpful, because in order to prove that something is in the spectrum, so the complement of that resolvent set, we could derive contradiction assuming that we have boundedness of the resolvent. Now the last consequence we will discuss of last consequence of Bayes' theorem is called the closed graph theorem. So what does the closed graph theorem tell us? It tells us that if we have a map between two Banach spaces that is linear, and we consider its graph, which is the set in x cross y of all those points of the form xt of x with x in x, then this graph being closed is equivalent to T being a continuous map. So that gives us a practical criterion to check whether or not the map is bounded by checking that its graph is closed. Now let's prove that. So there's an easy direction, which is not the one that I was talking about as being useful, namely the criterion, but the other way. So if I have a map that is continuous, then of course its graph is going to have to be closed. And why is that? Well, if I have xn that tends to x, and I have t of xn that tends to some y. Right. So I take a sequence in the graph, and I assume that this sequence converges in x cross y, and I want to show that the limit is in the graph. Well, what can I say? Well, I can say that t of xn will have to converge to t of x by continuity. Okay. And so by uniqueness of limit, I need to have t of x equal to y. And that means that xy, that point, is actually of the form xt of x, and so is in the graph. Right, and that proves the easy direction. Now let's have a look at the more interesting opposite direction. And it uses a very interesting technique that can be used in conjunction with the open mapping theorem. So what you do is you define a new norm. So you define the graph norm. So you define the norm of x adapted to t to be the norm of x in the Banach space, x where it lives, plus the norm of t of x in y. So that's really the norm of the pair x tx in x cross y. Now, I claim that x is complete for t. X is complete for t because if you converge in the, if you're Cauchy with respect to the t norm, then, well, in particular, you're Cauchy with respect to the x norm, and therefore you have to converge. So, since, okay, xn Cauchy for this norm implies that there exists an x in x such that xn goes to x, and there exists a y in capital Y such that txn goes to y. But because the graph is closed, y has to be t of x. That tells me that if I look at xn minus x in the t norm, well, I get xn minus x in the x norm, that goes to 0, plus t of xn minus x, but t is linear. In the y norm, t of xn goes to t of x, and so this entire thing goes to 0 as n goes to infinity. Okay, so now that we know that x endowed with the new norm, the t norm, is complete, therefore it's also a Banach space, we can consider a new map to which we're going to apply the open mapping theorem. So we consider an injection map, let's call it I, or maybe j to not mistake it for a complex number. Okay, that goes from x with the t norm to x with its standard norm that define it as a Banach space to start with. And that's just the identity between these two spaces, which are two Banach spaces. It's the same space, but different norm. Now, obviously, J is a bijection, right? It's just the identity map. And it's also a bounded linear map. Well, it's obviously linear. And it's also bounded because J of x is what? So the norm of x is certainly smaller than the t norm of x, because the t norm of x is the norm of x plus the norm of t of x. So J is continuous. So J is a bounded map between x endowed with the t norm and x with its standard norm. Okay, so what does the open mapping theorem tells me? Well, or more precisely, its corollary. It tells me that J minus 1, which is also the identity but going the other way, has to be a bounded map between x and x endowed with the t norm. And that tells me that the norm of x in T has to be smaller than a constant, namely the norm of j minus 1 times the norm of x in X. And what is that saying? It's saying that the norm of x in X plus the norm of T of x is smaller in Y. It's smaller than a constant times the norm of x in X. But that means in particular that the norm of T of x in Y is smaller than norm of j minus 1 times norm of x in X for all x in X. And that's exactly saying that T is a bounded linear map, which concludes the proof. Now notice that I've used the open mapping theorem in order to show that two norms, the T norm and the standard norms, are equivalent. And that's a very classic use of that